Today we'll be talking about flow. Flow is the quantity of fluid passing a point per unit time. Fluid can either be a gas or a liquid. Then different units exist to measure flow, but the unit normally used in medicine are liters or milliliters per minute or hour. So it's either 10 milliliters per hour or 10 milliliters per minute, and hence so. The flow can either be laminar flow or it can be a turbulent flow. In laminar flow fluid moves smoothly with molecules of the fluid moving in parallel. It is usually present in smooth tubes at low flow rates. Fluid can be thought as moving as in concentric ring, whereby the fluid in the middle moves the fastest, or twice as fast as the fluid on the side. This is a small video I would like to share.
Sometimes, when we look at flowing liquid, we can observe an interesting phenomenon called laminar flow. This phenomenon occurs when liquid flows so smoothly and steadily that it appears as though it's not moving at all, even though the liquid is actually flowing. This happens because each liquid molecule follows the path of the previous one with such precision that the liquid flows without any disturbance.
The other form of flow is turbulent flow, where the flow is turbulent and molecules move in different currents and vortexes or swirl around. Turbulent flow is most likely to occur in irregular tubes, at a constriction, at a corner, or at nervings, or when the flow rate is just very high. Turbulent flow is less efficient, and conversion from laminar to turbulent flow in a tube will reduce the flow of a given pressure drop. Another picture that describes a laminar and turbulent flow. You can see how the flow here is smooth, everything going smoothly. And then once there is a narrowing because of this particular dam, the flow becomes turbulent. We have a formula to help explain this all. It's called the Hagen-Poiseuille equation, where flow rate Q is equal to flow rate is equal to pi multiplied by pressure multiplied by the radius of the tube to the power of 4 divided by 8 viscosity, 8 multiplied by the fluid viscosity multiplied by length. The important thing to know about this equation is which of those factors have the highest impact on the flow rate. And the highest factor with the highest impact on the flow rate is the radius. The larger the radius, the more flow rate we get out of it. The next thing I would like to point out in this equation that in the formula we're using fluid viscosity, which you need to be careful that we're saying viscosity, because after a while we'll deal with another formula that doesn't have viscosity but rather have density. Hagen-Poiseuille equation, laminar, it describes the laminar flow in Newtonian fluid. And Newtonian fluid are fluid that are having constant viscosity in a tube. The formula is written in that way. Therefore, flow is directly proportional to any changes pressure and inversely proportional to the length and the viscosity of the tube. A simple example to help describe it is giving intravenous fluid rapidly. When we choose to give it rapidly, what options do we have to make fluid move more rapidly through an IV canal? It's either by increasing the pressure on the pressure back or by using a wider bore cannula. Any increase in those two things will increase the flow. And when we look to the inverse relationship to the length and the viscosity, the less viscosity and the less length the tubing has, the more flow we will get out of the setup. And that's why infusing normal saline is probably has a higher flow rate than infusing blood or infusing albumin or something that is more viscous than normal saline. But always remember the single most factor that has the greatest impact is the radius. Hagen-Poiseuille equation is much more discussing the laminar flow. When we move to the turbulent flow, we're talking about the Reynolds number. The Reynolds number is a dimensional number which predicts whether this flow is going to be laminar or this flow is going to be turbulent. So we end up with a number. Any number above 4,000 is probably a turbulent flow. Any number below that, below 2,000 is a laminar flow. And between the laminar and the turbulent, between 2,000 and 4,000, it's a mixture of both. So the formula for the Reynolds number, Reynolds number is equal to fluid density multiplied by fluid viscosity multiplied by tube diameter divided by viscosity. Density multiplied by velocity multiplied by tube diameter divided by viscosity. Note that in the Reynolds number, we are using diameter, not radius. And note that here, the factor with the greatest impact is density. I'm just referring to the point of density and viscosity multiple times because that's a question found in some books. And it helps to explain a very common example that I will describe now. Another place where flow is important is understanding the work of breathing. Turbulent flow is much more inefficient in comparison to laminar flow. So for airflow smoothly from the nose, going through the upper airway down to the bronchioles, it's usually the flow through the upper airway is a classical turbulent flow. So by decreasing the density of air or the inhaled agent, you can help reduce the Reynolds number and help maintain a more turbulent airway flow. A simple example is in the case of upper airway obstruction. If you're having a child or an adult to help improve the work of breathing is using heliox mixture instead of normal air. Because normal air, we're talking about a mixture of 70% nitrogen and 30% oxygen. But when mixing heliox, which is 30% oxygen and 70% helium, helium is much less dense in comparison to nitrogen. So the mixture is very much less dense. So the Reynolds number tends to go down and obstruction is not relieved, but there is less work of breathing and the patient can get oxygenated. Moving to the next section of the lecture. The next section, we're talking about some physical principles that can be manipulated in the equipment that we use. The first one is the Bernoulli principle. Bernoulli principle, the Bernoulli effect, is demonstrated when a fluid flows through a constriction in a tube or over an aerofoil surface. The first law of thermodynamics is that energy is always the same. It just changes from one state to the other. Fluid flowing down a tube displays two different types of energy: the kinetic energy of the fluid, as demonstrated by how quickly it is flowing, and the potential energy of the pressure drop across the tube. At any narrowing in a tube, fluid velocity will increase. Therefore, the fluid kinetic energy increases. To compensate and keep the total energy the same, the potential energy must therefore decrease, manifesting a pressure drops. This is a small video too.
Let us put the lower end of the tube into the vessel with colored water and blow the pipe again. We can see that the water makes a 30-centimeter rise. We'll connect the pipe to the blower, which provides a far higher speed of the airflow. We switch on the blower, and what we get is a perfect water sprayer. Now let us attach a plastic bottle to the pipe and switch on the blower again. That's incredible. A decrease in the internal pressure.
So what happens in Bernoulli, the Bernoulli principle is, I repeat it one more time, the energy is the same. A flowing fluid will have potential energy and kinetic energy. As we're reaching a narrow point, the kinetic energy will increase and the potential energy will decrease. This causes some form of negative pressure that is expressed as Bernoulli principle. So how would we use Bernoulli principle? One of the ways to use this principle is through the Venturi devices. The Venturi principle or the Venturi devices are devices that uses the Bernoulli effect by having a constriction in a tube that gradually decreases in cross-section area, then increases again. The pressure drop created can be used to entrain another fluid into the tube. An example of this are the fixed performance oxygen mask, also known as Venturi mask. It's also used in Sanders injections. It's used in scavenging equipment, and is used to humidify gases and to entrain liquid in nebulizer. These are a picture of the Venturi effect. This are a picture of the Venturi oxygen mask. Which, as described, there's a narrowing followed by an opening or a decrease in or increase in diameter. This causes entrainment of gases from the environment into the flow of the gas. Jet entrainment occurs when a high-speed jet of gas, for example, oxygen, pulls air along with it due to the frictional forces created by the moving oxygen molecule. In essence, the injected gas drags the surrounding air with it. This is the main principle of the Sanders injection. The total entrained flow is due to both the Bernoulli and jet entrainment effect. The last physical principle we want to describe in flow is the quanta effect. And the quanta effect describes that any fluid coming in contact with the curved surface will cling to the surface rather than follow a straight line of the original direction. This is due to the solid stationary curved surface creating friction between itself and the fluid, and therefore having a drag effect on the layer of fluid closest to the solid surface. This in turn has a drag effect on the next layer of fluid and so on, pulling the layer into the lines of the curved surface. So in short, if we're having a flow of fluids or a flow of gas, and there is a curved surface, and due to the frictional forces between them, instead of the fluid continuing in its straight line, it tends to move along the curve. This is a phenomenon that can be explained, that explain the maldistribution of air in the pulmonary tree after constriction. And it has also been implicated in myocardial infarction, where coronary arteries proximal to a bifurcation causes blood to flow down one limb of the bifurcation and omit the other. Okay, the quanta effect can be used to make valve mechanism with no moving part. If two tubes connected to a separate fluid supply are resulted at right angle before a wide junction in a tube. The third part of our talk today, we're going to talk about how to measure flow. One of the basic ways to measure flow is the rotameter. Rotameter are fixed pressure variable orifice flow meter. These are the types of devices that are measuring flow in our anesthesia machine or in our regular oxygen supply. It's usually a bobbin or a ball supported in a tapered glass or plastic tube by the gas flow being measured. An equilibrium is reached at different flow rate where the force of the gas pushing up the bobbin is matched by the weight of the bobbin. A gap exists between the bobbin and the tube wall. At low flows, the gap is small, the tube wall are essentially parallel, and the gas flow is laminar. Gas flow is laminar, it depends on viscosity. At higher gas flow, the gap is much higher. The flow can be turbulent, and thus the measure is measured on density. Just always ensure that there is some safety feature in our anesthetic machine rotameter. Always oxygen is placed, and this was some of the safety feature in an anesthesia machine. So oxygen is the last gas to be added to the fresh gas mixture. This is to avoid any hypoxic measure being delivered to the patient in the event of a cracked rotameter. The oxygen and nitrous oxide rotameter knobs are linked so that we cannot open nitrous oxide independent of oxygen. Oxygen can be left on, can be turned on its own, but nitrous is always turned on with oxygen, which is an anti-hypoxic safety system. Remember that electrostatic charges can build up in the bobbin, especially at low flow rates, which can result in a bobbin sticking and giving you a less accurate reading. The insides of the tubes are coated with clear conductive coating, or have a conductive strip to conduct away any electrostatic forces that build up. Rotameter or gas specific, they cannot be used for different gases because the level of how the rota will go up and go down depends, as we said, on the viscosity and the density. So each rotameter should be fixed to a specific gas. Another way of measuring flow is the Benedict Roth spirometer. It is a basic setup of measuring flows. Then we have the Vitalograph, which is the weak point of the Vitalograph is that it only measures expiratory values. Vitalograph is a set of bellows that are used to measure gas volume. The top plate of the bellow pivot and the notion is routed by a pin and a shart. The shart is motor driven and automatically start as the patient or as the examiner blows in the tube. The advantage of the Vitalograph is that it's much smaller and therefore more portable than a Benedict Roth spirometer. Its disadvantage, it only measures expiratory volumes. It only measures limited gas volume up to a few liters. And they are operator dependent, that if the examiner didn't follow the instruction perfectly, you'll probably highly affect the reading. But a much more practical option of measuring flow in our practice is using a spirometry. A right spirometry allows you to measure tidal volumes in anesthesia. It consists of an inlet and an outlet and a rotating fan in the middle that is surrounded by slits that direct the air in circular motion to return the van. The van is limited to as attached to a pointer, which displays the gas volume coming in and out. Gas flow rates can be derived by averaging the tidal volume over a period of time. The limitation with the right spirometry is that it's a one-way system, so it can only measure flow in one direction. It's either inspiration or expiration. And during anesthetic practice, it's usually placing the expiratory limit of the breathing circuit as close to the patient trachea as possible. The right respirometry is only accurate to approximately 5 to 10% and its accuracy varies with flow, and the accuracy is affected by the water vapor, electric charges that build up in it. Okay. The final thing that can be used is using a pneumotachograph. A pneumotachograph measures gas flow. From this, the gas integrates to a flow signal over the duration of inspiration and expiration. And this is then calculated. A pneumotachograph is a constant resistant variable pressure flow meter. The screen pneumotachograph contains a gauze screen that has a sufficient diameter for the gas to move through with laminar flow. When the gas flows through the screen gauze, there will be a pressure drop that is measured by 2 pressure ports on either side of the gauze screen. Because the resistance is constant, any change in pressure is proportional to the gas flow. The pressure change is measured by a transducer, which then converts the pressure into an electrical signal, giving us the readings.